Before we bring on the next team, I wanted to quickly run through the agenda. And so we'll have the University of Florida Gator Cooling, if you want to come up and start to set up your presentation. And right after that team presents, we'll go into a short break, make sure that everybody stretches and get a little bit of more coffee. And then we'll come back and have the final 3 presentations on the back end before lunch. I did want to make one comment, and maybe for those in the room who've not necessarily been part of the program in the past, one of the main things that we try, the basis of the C-AACE here, is to look at these projects specifically for a non-communist Cuba. So as we try to implement these projects, it would be specifically after a political different field. So as we look to change the methods and implement new infrastructure, the thought would be that the country in itself would certainly be more open to integrating some of these projects and roadways and the like. I did want to make a second comment that our viewers from the live casting are coming all the way down from Cuba themselves. And one of the comments that we just read was specifically, how are these infrastructure projects going to be done? And it's great to have Cubans outside of Cuba really looking at a solution for their current problems. So there's some other crazy stuff that they're saying, but it's certainly nice to hear from them in El Diario de Cuba. So without further ado, we'd like to welcome the University of Florida team, Gator Cooling. Their team is represented by Mr. Ryan Miller, Carl Guru, Louis Chong, and Diego Hitch, with their mentor, their industry mentor, Ms. Maggie Giraldo. They will be presenting on evaporative cooling containers for agriculture transportation. So, thank you.
Good morning, everyone. Thank you guys for coming out and listening to all these different presentations. We are the Gator Cooling team. I'm Luis. This is Ryan, Carl, and Diego.
Food waste is a major problem in both developed and developing countries throughout the world. Currently, 50% of the food being produced is wasted, which equates to $1 trillion per year. According to the FAO, or Food and Agricultural Organization of the United Nations, 49% of produce is lost during transportation in Latin American countries. Fruits and vegetables are wasted more than any other food product. Cuba is currently utilizing 58% of its land for agriculture, yet 70 to 80% of its consumable produce is still being imported.
Our design attempts to improve Cuban infrastructure by utilizing a shipping container that uses both convective and evaporative cooling, as well as a solar radiation protection, in order to decrease shipping temperatures and maintain a more constant shipping environment for produce. Our design reduces temperature, which decreases microbial activity, as well as reducing ethylene production and reducing respiration, which decreases food spoilage.
So a little background information on Cuba. There's currently 11 million people, according to the most recent census, living in Cuba, with an average annual temperature of 21 to 27 degrees Celsius and an average annual high temperature of 26 to 32 degrees Celsius. According to the FAO, one of the most recent studies, an ideal transportation temperature for most produce is between 13 to 15 degrees Celsius. On this picture right here, we can see how the plantains are uncovered and exposed to solar radiation. This causing problems during transportation.
So in order to provide the best design possible, we came up with the following objectives. We wanted to maintain a shipping temperature of 18 to 20 degrees Celsius within the container. Although this is not within the range that Diego just stated of 13 to 15 degrees Celsius, a 10-degree drop in temperature usually yields to about a 2 to 3-fold decrease in food spoilage. Secondly, we wanted to decrease the total amount of food spoiled by about 10%. Finally, we wanted to maintain the cost of this container under $1,000 in order for it to be more easily implemented by Cuban farmers.
Our design will reduce the amount of produce lost during transportation will increase the value and quality of produce and will increase profits being made by farmers. Ultimately, this design is going to lead to a reduced need for importation of fresh produce within Cuba. The values highlighted are showing the amount of money that can be saved per ton of produce. These are in US dollars but are in relation to the costs actually found in Cuba, not the United States. Assuming that the average flatbed truck is capable of holding 10 tons of produce, this means farmers are going to be able to save $200 to $3,000 per trip. Our design had 4 engineering principles, 3 related to temperature reduction and 1 related to pathogen reduction. Solar radiation protection, evaporative cooling, and convective cooling will all help to cool down the produce, while chlorinated water will be used in a fine mist water spray to reduce the amount of pathogens found on the produce itself. Solar radiation is a key source of heat resulting from the sun's rays hitting the produce. It is known that 950 watts per meter squared of solar radiation can affect produce during transportation. Current methods being utilized in Cuba are not accounting for this. By utilizing our design, which covers the produce, and painting the exterior of the container white, this 950 watts per meter squared will nearly be eliminated from becoming an issue.
Evaporative cooling is what makes our design unique and helps reduce temperature even further. The annual wet bulb temperature of Cuba is 25 degrees Celsius, and this can be reached through evaporative cooling alone. A water tank attached to the side of our container will hold up to 198 liters of water, and this essentially means that it can go in transportation for up to 6 hours of water being dispersed into the fine mist spray. The way it works, the incoming hot air will come in contact with the fine mist spray and then cause an evaporative effect inside of the container, decreasing the air temperature inside and cooling the produce altogether. It's similar to when your body sweats and there's water droplets in your body. The water droplets evaporate the outside air and cools out the contact of the skin. This is the convective cooling effect that will occur as the incoming air comes through and over the produce. The incoming air will go through the air deflector and cause a convective cooling effect inside, cooling the produce, and an extractor fan will then remove the excess air. Whenever produce respirate, they actually emit heat also, and the respirator or the fan will help extract that to cool the inside of the container as well.
So one of the final ways that we wanted to reduce pathogen buildup was by implementing chlorine into our water. So we wanted to dope the water with chlorine, so when it's misting over the produce, it'll be able to kill pathogens. According to the FAO, if we were to keep the chlorine concentration between 50 to 75 parts per million, this would be suffice to kill any buildup and maintain our container clean as well.
In order to select the best design possible from our original models, we came up with an equivalent systems equation where we take the parameters of both price, effectiveness, and the time to build the container. And we came up with the final design here, which is one long scoop that covers about 90% of the total surface area of the top, because it received the lowest score from our equation and weighing factors. Basically, as Luis and Diego stated earlier, this is a small model of how the container would work.
Let's use the microphone. Sorry.
This is basically a model of how the container would work. Air would come in through the front scoop while the truck is in motion, and it will direct the air on top of the produce, thus reducing the heat within the container. While the truck is stopped, however, there is no ram air going in through the deflector. Therefore, we implemented this fan that simulates the movement of the truck, thus allowing further convective cooling due to the sprinkler system that would be in the front of the scoop, as well as the convective cooling on top of the produce inside and out the back through the slits on the fan.
In our testing, we had the fan to be programmed at a 25 degrees Celsius measurement to be turned on. This does not necessarily have to be used, but it was used to improve our test readings. After our testing, we were able to determine that our objectives were met and the internal temperature of the container was able to be decreased by 6 to 8 degrees Celsius. It began at 28 degrees Celsius from a temperature control room because that resembles the relative humidity temperature in Cuba, and then it was able to be decreased to 20 to 23 degrees Celsius after our testing. The fan was actually able to keep the temperature lower than 25 degrees Celsius throughout the entire testing parameter, so it shows that it was an effective method of testing.
So we have estimated that our design will cost about $860 to implement. This can be compared to a refrigeration trailer, which would cost about $14,000, or a refrigeration truck, which would cost about $60,000. Our design is a lot more cost-effective and can be easily implemented and can easily cover its cost of build and implementation within 1 to 2 trips, depending on the produce that's being transported.
When edible food is wasted, more must be produced. This means more water must be used, more energy must be used, and more fertilizers must be used. According to the FAO, 65% of the water being used in Cuba is going towards agriculture. 7.5 million gallons of petroleum fuel are used each day, according to international energy statistics. By wasting more food, agriculture is also intensified. This means more land is cleared and more fertilizers are used. Cuba is currently utilizing 179,000 tons of nutrients in nitrogen, phosphorus, and potash fertilizers each year, according to the FAO. In addition, Cuba's agriculture alone produces 11.6 million tons of greenhouse gas emissions each year. By utilizing our design and reducing food waste, Cuba will use less water, will reduce its energy impacts, and become a more sustainable country with a more sustainable agriculture system.
So that concludes our presentation. At this moment, we'd like to acknowledge Dr. William Pelletier, Dr. Richard Schultz, Dr. Eric McElmore, Dr. Ray Buckland, and C-AACE for giving us this opportunity to present our design. And we'll take questions now.